Hey, Tony. All right. Well, it looks like we have most people who are going to join. Thanks a lot. This is the first Open Specky training. Very excited to see all of y'all. And let me know what you would like to get out of this, as we continue to do these workshops. I'm thinking maybe once a month for an hour. There's two different training sessions scheduled for today. So one's in like 12 hours. And I just did that so that way people from around the world could join, because we have colleagues out in Australia who want to use OpenSpecky, and pretty much the only time that works for them, for example, is like 8 p.m. my time. So just wanted to make it as accessible for people as possible. But it's going to be the same exact content in both meetings, so don't feel like you need to stay up until 3 a.m. to catch the latest and greatest on OpenSpecky. If that if that other time doesn't work for you, just make it to one of them. And these meetings will be recorded too. I'm thinking about starting these from like 0 to hero. So today we're gonna really start at a very basic level. We're just gonna do like single spectra analysis, talking about how to upload spectra, how to interpret spectra, how to look at spectra. In future ones, we may do some other more advanced processes, advanced batch analysis or spectral map analysis, things like that. So, okay, we still have some folks that are joining in, but looks like we're getting pretty close to having everybody. So, cool. So what I'm gonna do, I'm gonna start by just sharing my screen. If anybody has any questions at any point, please raise your hand. We only have an hour together today. Normally I would do like some intros too. So if you want to introduce yourself, just post a comment in the chat and say what's up, where you're from, what kind of spectra you like the most. And I will share my screen and you can follow along. I'm going to use the web app to do this, but there's a chance that when everybody logs on to the web app simultaneously, it starts to get bogged down because this is running on a single server. And so if that happens, what I'll do is I'll run it locally on my desktop. You can try to follow along on the web app. If it doesn't work in future meetings, I will allocate a much larger server. But I'm hopeful that we're going to be able to make this work. I know I've been doing a bunch of these workshops lately, and when I have like 20 people in the same room together, all logging onto the website, it does get a little bit slowed down. So if you notice anything like that, sorry about that. I'll fix it for the future meetings. All right, so let's see here. Okay, I think that everybody can see my my browser now. Let me just close some of these tabs. So to get to the OpenSpecky website, you're just gonna go to openspecky.org, and then that will route you to the main website, openanalysis.org/OpenSpecky, which is here. Open Analysis also has a bunch of other apps. So if you're a microplastic researcher, my main specialty is really developing web tools for doing microplastic research. So if you go to openanalysis.org, we have a bunch of other cool tools that we've been working on, like microplastic data portal, trash taxonomy, an image explorer, tons of things. These are all open source tools, which means that the source code is openly available. The data sets are openly available. So if you want to take one of these tools and use them for a different purpose, just reach out to me. and I can point you toward the source code. So in the OpenSpecky interface, you will see this. This is like where the vast majority of the analysis happens, on the Analyze Spectra tab. There's also an About tab that goes into if you want to get into some detailed instructions or get a refresher video about how to use this tool. There's videos in here. We have a very detailed um, description of the app also at, let me see, is it linked in here? Let's see this. Yeah. So if you click the SOP, if you prefer more like written down instructions on how to use the app, we do have documentation for that here. And these other tabs are just about different ways that you can collaborate with us. So the first thing that we want to do is get our Spectra ready. You don't need to use this test Spectra. I'm going to use the test Spectra today, but if you want to use your own Spectra, go ahead and pull that out. OpenSpecky currently supports a bunch of different file formats. One of them, the best supported one, is going to be the CSV. So this is what a CSV file looks like. It's called a comma separated value. And you can open these up in Excel. I'll just do that because I think a lot of people are more familiar with using Excel. And so in this CSV file, it's basically just a spreadsheet with one column labeled wave number and the other labeled intensity. And every single row is a absorbance value at that wave number, basically. A lot of spectroscopy software will allow you to export data as a CSV. If you're having any challenges with your file formats not uploading into OpenSpecky, I would recommend going to this tutorial here on file conversion in SpectraGriff. SpectraGriff is another open software that's a little more general purpose, and they've figured out how to crack these different proprietary file formats really well. Some of these file formats are just super challenging to open up and read in because there's no description on how they can actually be read into a computer. They might be encrypted. And so basically the people who are developing open tools for analyzing proprietary software, we're reverse engineering their data formats. And we're like reading in the binary basically to be able to get it read into OpenSpecky. So occasionally there's some challenges with file formats. Like I know SPA has some challenges. .0 can have some challenges, but SpectraGriff is pretty dang good at getting around those. So if you upload your data into SpectraGriff, you can follow these instructions and export it as a CSV file or a JDX file or a SPC file, and one of those should work in OpenSpecky. All right. For those who just joined too, we're just getting started. If you have any questions at any time, feel free to raise your hand or put a message in the chat. And if anybody would like to introduce themselves, go ahead and put a message into the chat. All right, so let's get started with our first spectrum that we want to analyze. So this test data set is a Raman spectrum of HDPE. All right, so we're going to click the browse button here. Yeah, it's bogging down a little bit. Thanks, Suzanne. All right, right, and then we're gonna upload the test data set here. Ooh, it is bogging down for me. I may need to run this locally. Let's see. Okay, yeah, other people are having some issues right now. Yeah, sorry. We're overstretching the bandwidth of the OpenSpecky tool right now. So if you're experiencing like Lauren, what you're experiencing right now is due to the bandwidth of the web app. Basically, what's happening is the web app is being run on a small computer that is connected to all of our devices right now, and all of us are trying to pull from it at the same time, and so it's slowing down. I basically have to increase the size of the server, and it's going to take me too long to do that during this call. So what I'm going to do is I'm going to run this locally for myself. That way folks don't have any issues. And you can if you use R, I'll show you how to run it locally too. And then in future meetings, I will allocate a larger server size, so then we won't have this issue. It takes a little bit of time. All right, so let me show you how to run this locally. Okay, so if you're familiar with R, there's a couple of things we can do here. So we're gonna read in the library OpenSpecky, and if you don't have that library, you can install it here. So you would just write OpenSpecky and then install that. I'm not gonna install it because I already have it. And then we're gonna do run app. And basically, this is the exact same thing as what people who are on their browsers are going to be seeing. So some of you probably have really great internet connection and are having no problem on the browser, and then others of us are getting a lot of lagging. This is basically going to be the same thing as what you'll experience on the browser, except for it's running on your local machine. And so running OpenSpecky this way is going to be a lot higher performance, and it's going to be a lot more consistent because the web app is something I'm updating constantly. If you run this run app on your local machine, you have control over when it gets updated, what's in it, all that kind of stuff. So this is probably the best way to run it, but I realize the web app is a lot more convenient for folks. So we can do the same exact thing, upload the Spectra to the Browse tab. And right away, what we see is that, so we have a couple of things turned on when I uploaded that. So the first thing was share your data. If you have that selected, your data will be shared to a community spectral database. And we're going to use that to improve the tool over time. If you don't want to share your data, that's totally fine. Just make sure this is deselected and your data won't be stored. Then pre-processing is also selected by default. This is really just to get you closer to your goal. I think that the main goal that users of OpenSpecky have is to identify their spectrum. And to do that, you really need to pre-process it. But I'll walk you through what this is from the start. So basically, if you deselect pre-processing, what you're going to have is your raw spectrum. And like I said, this is a Raman spectrum of HDPE. We have wave numbers here on the x-axis and the absorbance intensity here on the y-axis. The absorbance intensity for this plot is getting normalized from 0 to 1 by default, just so that it's kind of standardized every time that you look at it. Wave numbers are the number of waves of that wavelength that can fit into a centimeter. It's a very complicated thing. I don't know why this is the common way that the x-axis is in spectroscopy, but for Raman and IR, normally we convert wavelength to wave numbers, and then we reverse the order of the wave numbers. So it's from highest to lowest here. And what this is the reason we reverse it is that these high wave numbers are actually low wavelengths. They're inversely related. So these are low wavelengths, these are high wavelengths. I don't fully understand why wave number is used. It has something to do with like energy calculations for people who are like really deep into the physics of spectroscopy. I honestly I don't think about it too much. I'm more interested in how can I interpret and identify what this signal is. And so when you're thinking about that, most algorithms out there, they are looking for high regions. So they're looking for values with high numbers in your signal as very important values for identification. So what that means is that basically this high peak is going to be, when we try to run identification, this high peak is going to be the most important thing. Also, this region here is going to be very important because it's elevated, and these regions over here will be important too. There's one problem with this though, and that's that this region in the middle is not important. It doesn't have very sharp peaks. This is actually what's known as a baseline signal. So we have elevated baseline here. In Raman, this could be from fluorescence. This can also be from scattering effects. It could be from the focus of your device. It could be from different types of scattering, like me scattering. And there's a ton of different things that these baseline signals can be from, but they're not due to the chemistry of your material. That's the most important thing. They're really, baseline signals are often not what we're looking for. It's not the signal that we're looking for. So what we want to do is we want to make this region here low and all the sharp peaks really high. And when we click this pre-processing, it really does that. It automatically converts the spectra so that the peak regions are really big and the baseline region is really low. And so that's really that for most algorithms that are out there, Euclidean distance, correlation coefficient, they're really going to prefer this kind of presentation of the data. Because if you don't do this, what will end up happening is the baseline will actually get matched and identified material type, which is not what you want, because these baseline signals could be due to other things. One sec. I think somebody was trying to get in, and then not sure if did they get in.
Hey, Win, this is Shelly.
Hey.
I've been admitting people for you.
Oh, thanks. Okay. Perfect. All right. Cool. So, all right. So pre-processing, let's go through like some of the steps that we get to come to this conclusion of like what's a high quality processed signal. So the first thing that we can do is we can look at the impact from this smoothing derivative. And when we deselect that, it's basically removing our transformation on the spectra. So this is really the thing that is processing the spectra to have this presentation where the peaks are high and the baseline is low. And what it is so we can open up here and look at some of the details. So you have a few different things that you can calibrate here. The first one is the polynomial, and the smoothing derivative. This is the Savitsky-Golay filter. And what it does is it takes your signal, and at every point along the signal, it calculates the derivative, so the slope of that point, using a window of points around it and fitting a polynomial curve to those points. The polynomial curve order here is a third order polynomial. You could also use a second order. Those are kind of the most common ones that people use, but we have a wider range you can play around with. If you increase the polynomial order, so we can just play around with that here. Increase the polynomial order, you should get, let's see. It should become more, the fit will be more wiggly, so it should get more noisy, versus decreasing it should get more smooth. So this is one way you can smooth your spectra while you're doing this transformation. The derivative order, so this one, if you just want to smooth your spectra, then what you do is you set the derivative order to 0. That will make it, you're just adding in smoothing, you're not doing a derivative transformation. First order derivative is a pretty common one that people use. I wouldn't recommend, unless you're doing something really advanced, I wouldn't recommend going into second or third order derivatives. They are basically going to take the slope of the slope for the second derivative order. The third derivative, it's going to be the slope of that. And really, we need, if we're going to identify this spectra, we need to compare our process spectra to a library spectra that's been processed in the same way. And our libraries right now, we only have 2 flavors. Well, basically 2, a derivative one and a baseline corrected one. And we'll get into that here in a minute. Now the wave number window, this one is basically how wide that window is around the points to search, to calculate the derivative. And so if you increase that window, you should get more smoothing. If you decrease the window, it should be less smooth. I recommend for most cases just using the default, because you can see that what the signal looks like is changing based on how we change these parameters. And the default is set up so that it's in line with the library spectra. So for the vast majority of cases, I'm recommending to just use the default settings. Absolute value. So this one is going to take the absolute value of the derivative. And this thing, when I learned about this, I just thought it was such magic, because when you do derivative spectroscopy, this is what the slope actually looks like. And it's very hard to interpret. You can run identification procedures on this derivative transform, but for me, it is not very intuitive to look at this spectra. Whereas the absolute value of the derivative actually looks something more similar to what a really nicely processed absorbance spectrum looks like. So that's why we do the absolute value. Checking if there's any comments or hands raised or anything. Cool. All right. Conforming wave numbers. So this is another thing that you can play around with. You can change the step size. So if you zoom in here, you'll see, even though this is plotted as a line, it's not actually a continuous data set, there are steps. So it goes from 2744 to 2736. So every 8 wave numbers, there's a data point in here. Now, if you want that step size to be different, you can increase or decrease the wave number resolution. So increasing it up to 12, you'll end up getting more. It'll be less smooth spectrum. Decreasing it down to 4. Sorry, did I say that in reverse? This is going to be finer step size. So this is less smooth. And this should be higher step size, so it's more smooth. 8 is what all the libraries are processed with. So I recommend keeping it at 8. But these are things like you can use OpenSpecky to do identification, or you can use OpenSpecky just to process your spectra. So we have some fine things that you can fine tune if you like. All right. OpenSpecky assumes that your intensity values are in absorbance units. And so if you have percent transmittance or something like that, or reflectance, then you'll need to use one of these corrections for the best results. So I can just turn this off and you can see, that transformation will it'll invert your spectrum. All right, now we're getting to some of the interesting ones here. So I'm gonna turn off the smoothing and derivative, and I'm going to show you another technique for getting a similar result to that absolute first derivative. And it's called baseline correction. So the first derivative does something like baseline correction, where it removed this big bump in the middle, this signal that we're not very interested in. But there's another way you can do it without distorting the other peaks. So one of the issues with derivative is that it kind of distorts the shapes of these peaks. It can also amplify the noise. So in this region, even though we pushed it down, we actually increased how much noise there was. And each order of derivative you go into, it'll increase your noise. So there's a trade-off there. You get more noise, but you get this really cheap computational effect that's really good. So if you have high quality spectra like what we uploaded, there's no problem with the smoothing and derivative. But another way you could do it is to use baseline correction. And what this does is it just squishes the baseline down by essentially it fits a polynomial to the entire spectrum. And then wherever there are peak regions, it finds them because they'll actually be elevated above where the polynomial fit is. And it removes those, so then it can iteratively find the baseline here, which is basically, I'll just draw it on here for you. It's kind of hard to see actually. But this is essentially the baseline, and it will fit that line, and then it will subtract that from the spectra. And that's what you're getting here when you see this result. Now, this one, you don't necessarily need to keep it at 8. It's not that important. What's important is that you get a good baseline subtraction. So one of the issues here with this one is that we've created an artifact over here. So look at this region here and see when I click baseline correction, it makes a little peak over on the left-hand side. It's creating this artificial peak, and that's because the baseline polynomial didn't fit perfectly. Now, if we change this to be a little bit higher, that peak goes away. If we make it a little bit lower, that peak is also gone. But now we have this peak this little bump in the middle amplified. So this is something that you can play around with a little bit to get a high quality result. A lot of times higher polynomials will fit a little bit better, but there's a trade-off with them that they're really computationally expensive. So if you're running this in batch, which is I think where a lot of people are going with spectroscopy, and we'll be getting into that in like future sessions. If you're running this in batch, you really may have a challenging time doing baseline correction because it takes so long. I mean, it's probably going to take 10 or 100 times as long to do your analysis if you have like thousands of spectra. But in general, this is considered a higher quality spectral correction than derivative, because what this does is it retains a lot of the peak information, and it really just removes what you're not interested in looking at, and it doesn't have that effect where it amplifies the noise. So if you can do baseline correction, would recommend doing it. All right, range selection. So a lot of times we have regions of spectra that we are not interested in. And let's say over here, there's no peaks over here. I'm not really interested in looking at that, trying to identify that region of the spectra. What I could do is I could set the maximum wave number to 3000 and then turn this on. And now, oh, that's actually, that messed up the baseline correction though. That's a little bit better. Now range selection. So now we've cropped off that region. Similarly, you could isolate individual peaks that you're interested in. So let's say we just want to see the peak that goes from 3000 to 2700. So 3000, 2700. And then here we probably want to turn off baseline correction if we're doing that, because we're just looking at that single peak now. And there's really not a lot of baseline influences when you're looking at a small region. And so that's what that one peak looks like. And you could try to identify individual peaks by running it, doing range selection, and then running it against the identification. All right, let me turn that off. Okay, so that's one way to get rid of artifacts that we're not interested in. And another way is by doing this thing called flatten region. So this is more of something that we do in IR spectroscopy. The CO2 region of the IR spectrum is pretty problematic. It's really hard to remove. Oh, I just saw a question come in, sorry. For the baseline correction of hundreds of spectra at the same time, would polynomial level 8 be okay to apply to all, or would you go through each spectra individually? Great question. What I would do is if you were doing hundreds of spectra or thousands of spectra, I would try to figure out which baseline polynomial works well in general for your spectra first. So I'd start by uploading all of those spectra, pre-processing them, and trying to figure out, like, does 8 look good? Because certain devices, certain ways that you've collected your spectra are going to have different baseline signals. And so I would just try to figure out like what that number is in general, and I would click on a bunch of them. We'll go over batch processing in a future version. Typically 8 works well. I'll just tell you that it works pretty good. But you may find that after testing a few of your spectra that actually 10 is better, or 12 is better, or something like that. And then I would apply the same exact processing routine to all of the spectra. Great question, thank you. All right. So we're going to talk about flattening regions. So this is a Raman spectrum. We don't have the CO2 peak problem. The CO2 peak is between 2200 and 2400. So it's like somewhere over here. If you have an IR spectrum, you may have a big peak there. And a lot of times this peak can be the largest peak in the spectra. And we were talking earlier about how the identification routine really is just looking for the large peaks. It's just looking for the regions that are high. So if you have a huge CO2 peak and you allow that to remain in your spectrum, now you're just going to identify CO2. It's not the CO2 that you're interested in. You're interested in the material, but the problem is the signal of the CO2 has been collected while it's trying to collect the signal of your sample, because the light has to pass through the atmosphere, and there's CO2 in the atmosphere, and it has a really strong signal. So if you have these signals, which are very common in IR, it's a good idea to do a flattened region. And what that does is it just draws a flat line in that region. So here you can see this flat line that we're starting to draw here. There may be other applications for this. Maybe you have some other peaks that are kind of problematic and you wanna remove them. So you could always change this. Like let's say that this peak right here from 1328 to 1248 is problematic. 1328. Oops, 1328 to 12. So now we can remove that peak just by flattening it. So basically, if you want to remove peaks that are on the inside of the spectrum, then you'll use flatten region. If you want to remove things that are on the edges of the spectrum, then you use range selection to do that. All right, so we'll change this. So I'm gonna, before we do identification, I'm gonna just refresh because we've changed a lot of the settings, and honestly, I don't remember exactly which settings we've changed at this point. And if you refresh, it'll reset everything to the default. So we're just gonna refresh, and then I'll re-upload this. So what I want people to be able to do is to be able to identify their spectra as accurately as possible with as little effort as they can. And so when you're first getting started in OpenSpecky, what I want you to do is upload your spectra and then click this identification. And that identification, what it's doing is it's running a correlation between your spectrum and a library of 10,000 or more spectra. And this specific library that we're running against has been absolute derivative transformed. It has has Raman spectra and IR spectra in it. If you yeah, I'll talk more about the libraries in a minute. Okay, so we just ran identification. We identified against 10,000 or more spectra, and we can see the top match here. So our spectra is the white one, and the red one that's overlaying it is the most similar match. Now, this match, I'll tell you, is a very high quality match. This is almost an exact fit. This does not happen very often. If I see something that's this good, I say, oh, either something went really good or something went really bad. Because most of the time you're going to have a little bit more challenge than this. And why I'm saying that it's really good is that the peak location, so the high regions here, are in the same location as one another. They're the same relative height of one another, and they're the same shape. And so if you have those three things, the same location, the same relative height, and the same shape, then you're in good shape. That means that you have a high confidence match. Now, there are a couple of peaks over here that are not being matched. These peaks These, I believe, are real peaks, even though they're very close to the noise here. But they are not the same in your material as in the reference library. That is okay if you have a couple of small peaks that are not perfectly in alignment. We really are mostly interested in the majority of the area under the peaks being high quality matches. Now you can also go in and try to look at some of the top matches to improve your confidence in this. So here, the first, if you click more, the first match is HDPE. Second match is also HDPE. We can look at that one. Third match, also this one's LDPE. Fourth match here, we have another LDPE. All very high similarity. And so at this point, I would say, yeah, this is a polyethylene spectrum. That would be my assessment, and I would move on to analyzing the next spectrum. If you're happy with the top match, you can download this top matches data set. So you change this to top matches, click download here, top matches, and we'll show you what that looks like. All right, so the top matches is going to have all of the information about your library, the number one match for the library. If you want to start assessing more than just the number one, you'll need to actually go in and kind of fine tune which one you're trying to pull from. So it says library ID here, match value. So this is the strength of the correlation coefficient. And then it gives you way too much information about all the metadata that you could have about the spectra. And that's because this library has been developed by aggregating 30 different spectral libraries. And we're really trying to maintain as much metadata as we possibly can. Now, the main things that you'll probably be interested in is this material class here. If you're doing plastic pollution research, material class is really important because we have regrouped the classes to be relevant to plastic pollution. So we've put all of the polyolefins together, for example, because there's too many different varieties of polyethylene and they can't be identified, they can't be differentiated from one another very easily in IR Raman spectroscopy. The other thing you'll probably be interested in is the match value. Most of the time, you will be applying a threshold for this match value to determine whether or not you're confident in the match. So right now, this one's 0.98. That is very good. People go down as low as maybe 0.7 for their match threshold. And that's the threshold that we've selected here too. So you can use these columns here to quickly filter through your data if you have a lot of spectra that you've uploaded at once and figure out which ones are high confidence, which ones are low confidence. If you have spectra that are low confidence, then what you'll want to do is you'll either want to try to analyze them manually, or you'll give them an unknown label. So you'll say, I don't know what this is. There's nothing similar in the library. And it's really going to depend on, that decision is going to depend on your study goals. I like to use the example of some analyses. People will come to us and say, I just want to know is there any chance that there's plastic in my sample? And that kind of question, you should be using a really low match threshold, because it's okay to have some false positives. They're more concerned about false negatives. If you set a really high match threshold, you increase your false negatives. So that's just something to think about. It's a trade-off of where you put this match threshold. Decreasing it is going to increase your false positives, and increasing it is going to increase your false negatives. Okay, one question from Colleen. Any advice for tape possibly masking the plastic ID? Very good question. This is a really big challenge in sample prep. So when you're prepping your sample, a lot of times people will use like sticky tape or something like that. They'll put a particle down on the sticky tape, and then they'll collect the spectrum of the particle. But the challenge is that, let's say this is our particle here, and we have this big beam of light. It may pass through the particle, get to the other side, and then collect some signal from below and come back up. And so you can get signals from the tape below, or if you have tape coating the particle too, like if you accidentally like touched it to some tape and it's on the surface, now the signal of the tape on the surface is going to get into your signal. There's some different ways that you can deal with this. The first one is to remove that signal, and you do that by background subtraction. This isn't something that we currently support in OpenSpecy, but you can do this on most machines. Basically, what you'll do is you will take you'll take your spectrometer, and you'll make a background point that's on your tape, and then you'll use that background point to remove the background, both atmosphere and what's below your particle, from the spectrum that you collect on your particle over here. So that's one way to do it. But I will tell you, this is a little bit of a challenging thing to deal with, because if you're subtracting a background that has a strong signal from your particle background, sometimes that background signal is too strong, and it will actually overwhelm the subtraction. And so you'll get these like reverse peaks, basically, from your particle spectra, and it's a little bit inconsistent. So in general, this is more of something that you want to deal with on the sample prep and sample collection side if you can, because if you have to start going into like how exactly can I remove that signal, it's gonna be pretty variable, like how well you're able to remove it. So in general, what you want to do is make sure that the way that you've prepped your sample and the way you're collecting the spectra doesn't have that signal in it. And so what you could do is you could run your spectra that you're collecting against your tape spectra to see how similar it is. And if it's very similar, then you know that you didn't really collect your particle signal very well. So that's one way. Hopefully those are some helpful ideas. Happy to chat more about that if anybody has any questions. All right. Get back up here. Okay, so we got about 10 minutes left. I'm just going to talk a little bit about identification libraries here. So we use the default identification library. That's fine. The both derivative library. We also could have used the Raman derivative library for this, because that doesn't have FTIR spectra in it. It doesn't really matter that much if you put IR and Raman spectra together in the same library, because IR and Raman spectra are so unique. You shouldn't have like spectra that are being identified as the other one, but it occasionally does happen. And so telling OpenSpecy whether you have Raman or FTIR is going to be helpful. The other thing too, so we're using the derivative library here because we have the derivative, the absolute derivative transformed spectra. If we were using the baseline corrected spectra, so if we removed the smoothing derivative, I'll just turn this identification off so it doesn't keep running. If we turned off the smoothing derivative and then we turned on baseline correction and increase that so that we get a good baseline here. Then what we'll want to do is we'll want to use the no baseline library. So you always want to have your spectra processed in the same way as your library spectra. That's really the most important thing, is that those two things are in sync with one another. The library spectra and the unknown spectra are being processed the same way. So now we're using the no baseline library and we're able to identify this again as HDPE. Also very good match to the baseline corrected library. I can show you real quick what would happen if we did the derivative library. So if we ran the Raman derivative library, let's see, what did it identify things as? Interestingly, it still identified it as a polyolefin, but don't hold your breath for that one. It is not going to work every time. And definitely do not try to identify raw spectra that are totally unprocessed, for the same reason, because it will give you lots of inaccurate IDs, and some of them could even have high confidence. They could even be high correlation values. This one isn't very high correlation value, but sometimes you do get that. So yeah, this is the main issue with the mismatch here, is that these signals are not processed in the same way, and you can tell that by the fact that many of the peaks in a large area under the peaks are not being accounted for. They're not like perfectly overlapped. All right. Some other things here. So there's this correlation threshold that's turned on by default. This one, we put it at 0.7 because that's what we found to be high quality for OpenSpecy. If you have it above 0.7, this little indicator here should be green. It will tell you that the correlation is above your threshold. So like, for example, if we put this down to 0.3 or something, now it's green. And that could be a quick way to QA/QC your identifications. Make sure that they're high quality when you're going through things fast. Similarly, signal to noise is another important thing to be thinking about. So I'm going to turn this off, and then I'm going to turn baseline correction off. And I'm going to add in this thresholding signal to noise. So signal to noise is essentially the highest peak divided by a low region of your spectra where there should be baseline. And classical spectroscopy would recommend that this value is 10 or above. In reality, you almost never have 10 or above. So we actually set the default at 4, so that you have at least 4 times your peak regions, and your baseline regions are at least 4 times separated from one another. Now this currently is at about an 8, I think. So this one, I think if we put it to like 10, this is going to turn off. It's not going to be colored anymore. But if we add in so one of the issues here right now is that we have this strong baseline signal. If we remove that using baseline correction, now our signal noise value goes up. And so now we're above our threshold. I think now, I don't know what it is now. Now it's like 35 or something like that, signal noise. And so this is another way you can check to see how well you're doing in your pre-processing, is to look at the signal to noise, because if you're improving your spectral quality using your pre-processing routine, then this signal noise value should go up. So something else to think about when you're going through this analysis. Okay. I think I'm gonna pause there. I think that's all I want to go over today. If anybody has any questions, I'll also stick around for as long as people want to, so we can chat through anything. And I'll also mention again that we do have another one of these sessions in 12 hours, but it's gonna go over the same exact thing. It's just for people who are like in different time zones. And the next one will be, we're gonna do them on the 9th every month, unless that ends up falling on a weekend, then I'll move it. And y'all should have like a recurring invite to participate in that. Yeah, Tony.
Yeah, I just want to say thanks so much, Win, for taking this initiative, and also to lead these workshops. And for my part, I am literally going from zero. Although I've participated in microplastics research, I've never matched a spectra. Or in fact, prior to this workshop, I was just going through the procurement procedures to buy an FTIR and a micro Raman for Dalhousie. So it's really great to see this from scratch. So I'll be participating in future workshops. Thank you.
Thanks. Looking forward to it. Any other comments or feedback, or if anybody has any specific things they'd like to see in future meetings too, let me know. All right, sweet. Thanks, Sam. Okay.
Hey, Win, there's a question above Sam's comment about providing the recording.
Oh, okay, great. Yep, I will provide the recording afterward. I will share a link to that on LinkedIn, and I can also send it in the on the calendar invite. All right. Thank you. And I thought I saw a hand pop up, but then I lost it. So great to see everybody. If anybody does have questions or wants to stay on, feel free. I'll stay on a couple more minutes and chat, but if not, no worries, and hope you all have a great rest of your day. Thanks, y'all. Thank you.